In this video, we're going to discuss propagation of errors or propagation of uncertainty. In previous videos, we figured out how, if you've made a measurement, to estimate the uncertainty in a measurement, for example, a distance. We could either use the scale from our ruler and how well we could read it, or we could make multiple measurements and take the standard deviation. The question we want to address today is what happens when we have, for example, a rectangle and we want to measure the area and we have uncertainty in our measurements of both x and y. So we know that the area of a rectangle is x times y, and let's just say we know that the uncertainty in our measurement, we have an uncertainty of our measurement our x, sigma x, and our uncertainty in our measurement of y, sigma y. The question we have to ask is, how does this translate to an uncertainty in A, the area of the rectangle? So let's look a little geometrically. First, let's consider what happens on the right side here when we take sig x plus sigma x. What we see is the additional area we get is sigma x times y. It's that block on the right side. So it's the area of that rectangle, that red rectangle, which is sigma x wide and y high. Similarly, if we ask what is the contribution of our error in y, we see we get a block that's sigma y high and x wide. So the area of the top block is x times sigma y, and the area of the right block is y times sigma x. So the question is, you can see that the error in x gets multiplied by the y value, and the x error gets multiplied, and the y error gets multiplied by the x value. So what we know is that there's some uncertainty as a combination of y sigma x and x sigma y. So we know these are the values. The question is, how do we add them together to tell us about the uncertainty of the area? So one can imagine that you could just add them linearly and say, hey, the total area is the error in both of these things summed up. Or we could assume that they might on the average cancel out and just say, hey, it's the difference between these two that is the uncertainty. But in reality, because if the errors are uncorrelated, then we have to assume that they neither add in phase, which would be positively, or out of phase negatively. So let's consider this case a little more closely. So let's look at three cases. One where the errors would just add linearly. And what we know there is that this is too big. It's unlikely they both maximally add or maximally subtract. So this would be an overestimate of our uncertainty in the area. If, on the other hand, we took and subtracted them, we could see quickly that this is going to be, it's unlikely that if one is positive, the other is exactly fully negative. So this would be a minimal case. The third case is the most likely case. If they're randomly correlated, consider these like two vectors, and the most likely alignment for these things is perpendicular, not either parallel or anti-parallel. So the length, if you like, of the line in the first case, in case A, would just be the sum of the two. In case B would be the difference of the two. But the case which most likely represents the real answer is the one where we add the two errors in quadrature and we get the length of this vector, sigma total. The green line here in case C would be the square root of y sigma x squared plus x sigma y squared. Okay, let's take a little deviation from our path here and talk about partial derivatives. Now, you may have had these things in math and you may not have. If not, it's fine. We'll introduce them here and they hopefully will make some sense, and you'll see that they're pretty easy to use, partial derivatives. So what a partial derivative is where you take the derivative of a function with respect to one of its variables, assuming all of the other variables are held constant. This is distinct from the total derivative, where you assume that all of the variables can vary, and then you have to use the chain rule to do differentiation. What we're going to do, let me show you some examples, and you'll see that partial derivatives are easy to use and are simple. And we'll see why they're important for understanding the propagation of error. So let's go back to our example of the area of a rectangle being x times y, and we can say that the partial derivative of of a with respect to x is written with this curly d rather than a straight Roman d. So we say curly dA divided by curly d dx. So that's partial of a with respect to x, and that's different from the full derivative. So you can distinguish those two letters there and see how they look differently. So if we differentiate a with respect to x, assuming y is a constant, then we get partial of a with respect to x is y. Because if you differentiate x times y with respect to x, you just get y. Similarly, if we differentiate, we take the partial of a with respect to y, we get x. And let me give you an example which is slightly more complicated. Let's say we had a function that was a slightly more complicated function of x and y. And we said, let's say the function is x squared plus 3xy plus y. Then the partial of f with respect to x is simply the derivative of this with respect to x, this first term, which is 2x, right here, plus the derivative of the second term with respect to x, which is 3y, and the derivative of the third term, which is y is held constant, so the derivative of y with respect to x is 0. So this gives us our partial derivative. Now, let's go back and apply partial derivatives to understanding our propagation of errors. So what we found, adding the errors in quadrature for our area A, is we found the uncertainty in A was the square root of y squared sigma x squared plus x squared sigma y squared. Okay, let's rewrite this in terms of the partial derivatives. We can say that sigma A is the square root of the partial of a with respect to x squared, which is, as we remember, y, and the partial of a with respect to y squared, which we got was x times sigma x. So if you notice that writing it this way with the partial derivatives is exactly equivalent to writing it the way we wrote it the first time, because the partial of a with respect to x is y, and here we have y and that's squared, and the same with x and x squared. So we can generalize this to the propagation of error formula, which is that in general, if you have a function of some coordinates, x, y, z, you can have as many as you want, sigma of the total is the square root of the partial of f with respect to x squared, sigma x squared, plus the partial of f with respect to y squared, sigma y squared, plus the partial of f with respect to z, sigma z squared. And this is the propagation of error formula which we'll use, and let me show you some examples. Okay, so there's the formula again. Let's consider just adding two numbers. C is equal to a plus b. We have sigma a, we have sigma b. We want to know what sigma c is. What's the uncertainty in c? So what do? We apply the formula. We say sigma c is the square root of of the partial of sigma with respect of c with respect to a, and the partial of c with respect to a is just 1, because the derivative of c with respect to a is, this term is 1, this term is 0, it's 1. So we get sigma, so we just get 1 here, sigma squared. When we take the partial of c with respect to b, again we get 1. So we get 1 squared here, and that equals just sigma a squared plus sigma b squared. So pretty simple. And if both sigmas were the same, if we assume that sigma a and sigma, if we're measuring with a ruler and we have the same uncertainty, then the sigma of the total is the sigma of each individual one times the square root of 2. Okay, let's do a different example. Here's our formula again. Let's take, for example, we say that a is equal to a squared plus b squared minus c squared. And this could, for example, be the remainder squared of the uncertainty from the Pythagorean theorem, where you have a triangle with a side plus b side, and you want to see if it's equal to the hypotenuse. So let's see how we would do the propagation of error here. We say that sigma a is the square root of the partial of a with respect to little a squared, sigma a, the partial of a with respect to b squared, and so on. And if we go through, what we see is that the partial of this first term, the partial of a with respect to little a is 2a. The partial of this thing with respect to b is 2b. And the partial of this thing with respect to c is minus 2c. But notice that when I square this, it's exactly the same contribution as each of the other contributions. And again, if they all had the same uncertainties, then you could see that this thing would be just the square root of 2 sigma times the square root of a squared plus b squared plus c squared. This is how we use our propagation of error formula.